Hello everyone, welcome to this video. In this video we'll be studying about the order of a permutation. So we have a result regarding this. It states that whenever we wanted to calculate the order of permutation, we can do so by writing it in disjoint cycles, and then we can take the LCM, the least common multiple of the lengths of each of the cycle. So before understanding this theorem, let's see few terminology which would be helpful to understand this result, right? So this result is extremely helpful when we wanted to calculate the orders of permutation, and also when we wanted to calculate the number of permutations of a particular order. This thing would be more clear when we will be studying about various examples. So you already know what is the order of a permutation group. Suppose we are talking about the symmetric group Sn, which is the permutation group, right? So it has order n factorial. You know how we have calculated the same. We have done so in the previous video. So this represents how many elements, that means how many permutations are present within this permutation group. So if we are talking about Sn, it would have n factorial permutations present within this group, right? Next is the order of permutation. So here alpha represents the order of permutation, right? We call the order of permutation as n if we are able to have alpha raised to power n as the identity permutation. This thing we have also studied in detail in the previous video. Okay, next is the order of cycle. Now we have been writing the permutation in terms of certain cycles, right? We have learned about the cycle rotation of permutation group. So what is the order of that cycle? So actually, the number of times given permutation alpha is applied to a certain number. Now we have a cycle. From the cycle, suppose we select an arbitrary number. Now how many times do we apply alpha, the given permutation, on this element, so that when we move to the next element, we would eventually come back to this particular element. So this is how many times we apply this alpha so that we reach at the same cycle. This is what is the order of cycle. So for this thing here, let's understand. So mathematically this thing represents alpha raised to power n of a gives you back the element a, where a is any member of the given cycle. If that is so, then this n represents the order of the cycle. For example, if we have this cycle 1 2 3 4 5, right? We wanted to calculate what is the order of this cycle. For that, we may take any arbitrary member out of 1 2 3 4 5. So let's suppose we select the number 3. You can select any number, the result would come out to be the same. So suppose we select the number 3. Now we'll apply alpha onto the number 3. So when you apply alpha onto 3, the next element that you get is 4. Now again, on this alpha 3 we have applied, so it is giving us 4. So what is alpha 4? Alpha 4 is 5. So whole of this thing give us 5. What is alpha 5? Alpha 5 is 1. So whole of this portion is 1, right? What is alpha 1? Alpha 1 is 2. So whole of this thing is 2, right? And next, what is alpha of 2? Alpha of 2 is 3. So basically we get back 3. We started with the number 3 and we get back 3. And how many alphas do we have to apply? 1 2 3 4 5. So we can write this to be alpha to the power 5 of 3, right? This is equal to 3. So therefore in this case 5 represents the order of the cycle, correct? So we are repeatedly applying this thing. Now you can also notice that if we start from 3, you see how many times do we have to move? We have to move from 3 to 4, 4 to 5, then 5 to 1, 1 to 2, and 2 to 3. So in total we have to move 5 times in order to reach at 3. And exactly, if you notice, this is the length of the cycle. It contains 5 digits only. So therefore this is also a result which states that a cycle which would have length n would have the order n, and we have clearly observed this through an example that this is indeed true, correct? Now having known all these things, to understand the result here, let's see several examples how this result is true. So it states that the result here states that order of permutation that is calculated when it is written in form of disjoint cycles, and then we can calculate the length of each of the cycle. Then we can take the LCM of those lengths, and that is the order of permutation. Correct? So using this thing, let's see an example. The example is we have to find the order of the permutation, this one. So this permutation is given where we are given two disjoint cycles, right? First one having 5 elements, second one having 3 elements. So you see this permutation, this consists of two disjoint cycles. One has length 5, another one has length 3. So the order of permutation would be the LCM of this number 5 and this number 3. So that is 15. So therefore 15 is the order of the permutation, and this is as simple as calculating the LCM. So you see how easily we can calculate the order of permutation. Instead, previously what we were doing, we were just keep on multiplying the given permutation until we obtain the identity permutation. So this is not what we are doing here. We are using this result here. So the next question that is here is, what are the order of elements of S7? Now under S7 we have many elements. How many elements do we have? We have 7 factorial elements, that we already know, and it is equal to 7 factorial is equal to 5040. So in total these many elements. So to write down all the elements in notebook and then see what is the order and then perform the calculations, that would be quite lengthy process, right? So how do we then obtain the orders of elements? In order to know the orders of element, you should first know what are the elements. But we may use this result here without actually knowing what are the elements. So let's see how. We cannot calculate the, that is what I have told you right now, right? So what we do instead, we use this result which tell us that when we write the order of permutation in disjoint cycle, the lengths, taking the LCM of the lengths is the order, right? So using this thing here, what we can do, because here we know in S7 we have all the elements which are taken from the set 1, 2, 3, 4, 5, 6 and 7. So in total we have 7 elements with us. So these we wanted to see how many possible ways are there in which we can arrange these 7 elements by themselves. So that is 7 factorial, and those many elements are present in our permutation group, right? Now what we can do, we can write all possible disjoint cycle of element S7 without actually seeing which number belongs to which place. What we can do, we can make a 7 cycle out of the 7 digits, correct? We can make a 6 cycle and a 1 cycle so that we have complete cycle. Then we can make 5 cycle and 2 cycle. Then we can make 5 cycle, 1 cycle and 1 cycle, so that we have a total of 7, and the greater digit is written over here. Then we have 4 cycle and a 3 cycle. Then we have 4 cycle, 2 cycle and 1 cycle. So they sum up to give you 7 in total. Then we have 4 cycle, 1 cycle, 1 cycle and 1 cycle, so that 4 plus 1 plus 1 plus 1 is 7. 3 cycle, 3 cycle, 1 cycle. So basically what we are doing, we are writing all possible combinations that would add up to give you the final result as 7. So we started with 7, 7 plus 0. Then we started with 6 plus 1. Then it is 5 plus 2, then it is 5 plus 1 plus 1, then it is 4 plus 3, then it is 4 plus 2 plus 1, correct? So 4 plus 2 plus 1, then is 4 plus 1 plus 1 plus 1, that will give you 7. Then we have 3 plus 2 plus 2, right? This one. Then we have 3 plus 2 plus 1 plus 1, that will give you 7. Then 3 plus 1 plus 1 plus 1 plus 1, that will give you 7. Then 2 plus 2 plus 2 plus 1, that will give you 7. And 2, 2, 1, 1, 1, that will give you 7. And then we have 2 cycle, 1 cycle, 1 cycle, 1 cycle, 1 cycle, 1 cycle. So when you add up, you will obtain 7. Then you have 1, 1, 1, 1, 1 7 times. So that will also give you 1 cycle. So these many possible partitions would be there of the number 7. Now for these partitions, what we are doing here, we are just looking at the order here. For 7 cycle, the order would be just the LCM of 7. So that would just be 7. Next, for the 6 cycle and 1 cycle, we would look for the order of the LCM. Order would be the LCM of the length of the 6 cycle, which is 6, the length of 1 cycle, that is 1. So its LCM is 6 only. Next, we would look at the order as the LCM of the length of 5 cycle, which is 5, the length of 2 cycle, which is 2, so the LCM of 5 and 2 is 10. Similarly, we can calculate the LCM of each of the numbers here. We have 5, 1, 1 LCM 5, 4, 3 LCM 12, LCM of 4, 2, 1, that is 4, 4, 1, 1, 1, that is 4, 3, 3, 1 is 3, 3, 2, 2 is 6, 3, 2, 1, 1 is 6, 3, 1, 1, 1, 1 is 3, 2, 2, 2, 1 is 2, right? Then 2, 2, 1, 1, 1 is 2, 2, 1, 1, 1, 1, 1 is 2, right? And then 1 7 times is obviously 1. So you see, for different cycles we have the order listed, like either it is 1, either it is 2 or 3 or 4 or 5 or 6 or 7 or 10 or 12. So these many orders could be present within a permutation group S7 of all the elements, correct? So this is how we have calculated that within a group S7 the elements would have order 1, 2, 3, 4, 5, 6, 7, 10 and 12.